Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel about everything I want to talk about science and math. And today we are in AP Chemistry, talking about Unit 2 with the College Board model. And we're finishing up the notes. This is 2.7, talking about VSEPR and molecular and atomic geometry. Okay, so what did I do with the notes? Are they here? No. Are they here? No, they're over here. Where I was answering questions. All right, get to the right page where we stopped. I think this is pretty logical, but some students struggle with this a little bit, I'm going to be honest. Okay, so what determines the shape of a molecule? Electron pairs, whether bonding or non-bonding, repel each other. So they're negative and likes repel, right? Like things repel. So it doesn't matter if it's a non-bonding pair or a bonding electrons, they're negative and they're going to push each other as far away from possible. Okay. Each non-bonding pair, single or multiple bond, produces an electron domain. And I was trying to remember. My son teaches at Tech, and I think he calls it something else. I need to ask him so that when you go to Tech, you'll be like, oh, I know what they're talking about. Who in here is planning on going to Tech? There's always some, yep. If y'all go to Tech, don't take it too serious. He says that too many kids there let themselves be under too much pressure. You need to know that if you flunk out of Tech, it's okay. You can go to Kennesaw, be an owl, and have a very good time. So don't take it too serious. Okay, so here we have them. So there's a thing called VSEPR, and it predicts the shape by the pairs. So if we have two negative things, for them to get as far apart as possible, it's going to be 180 degrees. They're going to make a line. Does that make sense? If you have three, they're going to push as far apart as possible. They're going to make a Mercedes symbol, and it's going to be 120 degrees. If you've got four, it does not make a plus. You can get further apart than a plus by doing a tetrahedron. So everybody take a black ball out of your model kit, and I want you to stick 4 of the long gray bonds in it, and we're going to make that shape. Go ahead and make that shape. Okay. This is our tetrahedron, and the bond angles are 109.5. Now, on the AP test, remember I told you they don't make you memorize so much, they make you understand? And they're not going to make you memorize exactly these bond angles, but they are going to ask you conceptual questions about how will they change if a certain thing happens. However, they do make you memorize the names of these things. So I'll show you what you're going to have to memorize, but just know there is a memorizing part to this. Okay? So next is, y'all have got that built? You got your 4 on there? Okay, so somebody hold it up. So this is our tetrahedron. Notice every way you turn it, it's the same. So now set it on your desk. See how it's like a little 3-legged stool. Now turn it over, and it looks like the same exact 3-legged stool. It is the same all over. Everybody see that? And now there you have it. That's the secret of life. That's what carbon does. And because it does that, it can make millions of different compounds, and that's why you're a carbon-based life form. That right there, that's why, the tetrahedron. Okay, and also we're going to talk about something else it does called hybridization, which was on our beginning screen I forgot to talk to you about, but you didn't know about it anyway. All right, so then here's another one, and we're going to do something with that in a second. But here, this one is where you have like a line going straight through, and then the 3 one going around it. It's like you do this one and this one together. You take this one and shove it through the middle of that one. So here's another one, and here, this is why I have my dog toy, is to show these to you, help you conceptualize it. Now my dog toy is this one, where it is 1 going straight through and then 4 around. And my dog toy, everywhere I turn it, it makes the same exact shape. But this one is if I put two together and pretend like they're one, it makes the three going around and the one going through. Can y'all sort of see that? Okay, so being able to picture these is really important. This is going to help you understand geometry so much. Okay, so here we've got 90 degrees between the stick and the three. And then the three is the Mercedes-Benz symbol. So these are the 120 degrees. And then when I let it go, boink, they're all 90 degrees. Okay. All right. So let's talk about this a little bit more. We're going to break it down. We use electron domain geometry to help us predict molecular geometry. So let's talk about what that is. Your teacher is ready for you guys. I'm going to open the door. Take your stuff and you may leave. Thank you for visiting. I hope you're all inspired to be chemists when you grow up now after this touch of exciting chemistry. Okay? So our first structure, y'all already know. What's this kind of structure called? What is that? Starts with an L. Lewis. That's a Lewis dot structure, right? Okay, so this one right here has got nitrogen bonded to 3 hydrogens, and it shows the non-bonding pair. Do you see that? So this one is electron domain. Electron domain geometry. So that's that one. And then when you do your final shape, you don't show the lone pairs, but you can tell it affects the geometry. This lone pair is pushing those hydrogens down and away. Can you see that? Because it's a big old negative. It's more negative than these bonds. And so it's pushing them away, but we don't show that. That is called molecular geometry. Okay, so we're going to remember the electron clouds are negative. There's a hydrogen kind of positive. Oh, come on. But he is negative. Do I need to go back up? Was that too fast? Yes, I figured. It's just not letting me scroll just a tiny bit. Oh, how about that? Is that good? The first line is Lewis structure. They got cut off. Okay. So we're going to talk about how many of these negative blobs, imagine that, here's our negative blob, how many does it have, and then how many are bonding and how many are lone pairs, and what shape does it make it? Okay? So now what I want everybody to do is I want you to take your black ball that has 4 things on it, and I want you to get another one and stick 3 of your bonds into it. And then for that one that you get another bond and stick on the end. I want you to make something that is linear shaped, and what you're going to make is called ethyne. You're going to make an ethyne. So okay, so I want a triple bond. I want 3 sticks between my 2 black balls here. Make a triple bond. See if anybody can do it. Three of them. You're going to have to bend them. That's why I told you to use the long ones. Oh, Joseph is getting it. Okay, Joseph, hold that up over your head. Okay, everybody needs to, hey, look, I'll show the camera so they can see what they're missing. What Ella can see what she's missing later. Okay, so this is it. I'll put it in front of me so you can see it a little bit better. Whoop. So this is in a straight line. We have 2 carbons with triple bonds between them, which is holding them straight. And then we have these 2 sticks, and you can see that this is a straight line. Okay, now this is not exactly what we're going to be talking about there, but this is just a way that our model kits can make a very nice linear molecule. Okay? All right, so everybody made your linear molecule. Everybody can see that there's 180 degrees between those 2 atoms. Do you see it? Okay, so if you have 2 electron domains, So like here I have an atom that can make 2 bonds, and both of these are bonded, and we have no non-bonding. It makes a linear atom. So here we've got 2 B's and an A all bonded together, and the example they have for us is carbon dioxide. Now our model kit doesn't do so good of a job of showing that linear. Let me try to think. Yeah, it could. Okay, let's build that. Everybody leave all 4 long ones on one of the black balls, and then take 2 of them and put them in a red one, and 2 more in another red one. Red ones should have 2 holes. And you will be making a beautiful linear carbon dioxide. Isn't this fun? Little hands-on bit to it. Help you visualize with chemistry tinker toys, chemistry Legos. Joseph has it. Hold it up high, Joseph. That's what you're making. See how that's a line? Those 3 things are in a straight line. Here, let's show the internet land. Ta-da! Look at that. Didn't he do a good job? They are in a straight line, 180 degrees. Woohoo! There you go. All right, everybody kind of starting to see how that's linear? Okay, so let's do another one. So this one is like a boron. It has 3 electron domains, and the shape it makes is the Mercedes-Benz symbol. It's flat. It's got 3 things going on. So it has 3 blobs of negative, 0 unshared pairs, and the shape it makes is trigonal planar. And our example is BF3. So you can make that with your kit with, I think boron is tan looking, kind of gold. Yeah, I think that, does that one have three holes like that? Yeah. So you could do that. You could put 3 green balls on that tan ball, and you would have a beautiful trigonal planar model made. Everybody online can hear all the little parts hitting the table. The sound of learning. Oh, right here, look, I'll show yours to the video. You did a good job. So here's a beautiful BF3. Notice how it's that Mercedes symbol. Let's see if I can hold it in a way that shows, ta-da, trigonal planar. And these bond angles are 120. Okay. Beautiful. Okay. So now, what if instead one of these didn't make a bond but was an unshared pair? Okay. We would have 2 bonds and 1 unshared pair, and it would do this. But that unshared pair is still negative, and it's still going to push these away. But this is stronger than those bonds, so it's actually going to squish them a little closer together. And this is how they ask you on the AP test. They won't ask you what bond it makes, but it will say, is it going to be more or less than 120? And the answer is less. They're going to be squished closer together. It will be less than 120. And these bonds will be more than 120. Can you see that? So easy. AP Chem is not hard, is it? Our example of this is NO2. Okay. How are we feeling about that? Okay, let's go on. Okay, now you can look back at your tetrahedron. Our tetrahedron has 4 electron domains. If they all bond and none don't bond, you get the tetrahedral. So this is the thing I told you you have to memorize. You have to know the names: linear, bent, tetrahedron, trigonal planar. All of these are things you have to learn. And our example of this is always methane. That's our classic. But what if we only have 3? We have 4 domains, but 3 bonding and 1 unshared pair. The name of it comes not from the shape with the unshared pair. It's the shape if you ignore it, and that is trigonal pyramidal. because it's a three-sided base of a pyramid. So use the blue ball, and I think it should have 3 holes. And does it reflect this geometry? Can you make it? See if you can make the trigonal pyramidal. Stick 3 things out of the blue ball. And that should be, it's got 4 holes? No, it's got 3. Joseph has it. Let me show it to the internet. Okay, so this is what it looks like. It's like this little thing that can stand a little pyramid, but it has that you don't see a big blob of unshared pair right here on top. And that's what's pushing these bonds down and closer together. Did everybody get it? Excuse me, I need some more water. I've talked too much today. So our example here is NH3, and that's our trigonal pyramidal. Okay, now what if only 2 of these are going to bond? And 2 are unshared pairs. So we have 4 electron domains, 2 bonds, and 2 unshared pair. It does this, and that's bent. And our example for that is water. So everybody can make water. Get a red one and put 2 bonds out of it, and you've got water. And you'll see how water is bent. So it's based on that tetrahedron, but it's going to be shoving these hydrogens closer together. So is this bond angle more or less than 109.5? Less. You're starting to imagine it? This isn't hard, is it? Chemistry Legos. Okay. The effect of non-bonding electrons in multiple bonds, non-bonding pairs are physically larger than bonding pairs, and that's why they're big and they're more negative and they squish those bonds away. That's how you can think of it. Okay. Now, electrons in non-bonding pairs and in multiple bonds repel more. So the non-bonding pairs repel more than the single bonds. Now, this was something that I was getting questions from last period. And it's one of those things like I've just done it so long, I forget that y'all don't know this already. Okay, so what this is, see how it's a triangle there and a dotted line there? These are just lines, but they're trying to show perspective. They're trying to show this is a tetrahedron on a flat piece of paper. They're trying to make it look like this hydrogen is coming out at you, and that one's going back. So that dotted line means it's going back away from the page. And that's a 3D object, not 2D. Does that make sense to you? All right, so here they're all even, but then when you get the non-binding pair, it squishes these together more, and 2 non-binding pairs squish them even more. So this one, here we have also double bonds. Multiple bonds do this also. So here is this example of carbon double bonded to this oxygen, so that's more negative. Single bonded to the chlorine, it's going to squish the chlorines closer together. So this angle is 111.4, but these are 124.3. Now, it won't ask you these numbers, but it's going to ask you which bond angle is going to be greater, which one is going to be less. This is less because it's squishing away. These are greater because it's squishing that way. Yes?
So in the AP test, is it going to be open choice?
Is it going to be what?
It's going to be like response, or do you do open?
Both. So half of your test is multiple choice, and that counts half. And the other half is free response. So it's like 50 multiple choice, I think, but I'll look it up because I've looked at so many practice tests. I think I might have it wrong in my head. And then it's on the other half is like 7 free response, and they both count equal. And passing is like a 49. So if you got all the multiple choice right, you could get all the free response wrong and make a 3. But nobody can do that.
So is most of the free response going to be math?
No, that's the other thing, is the free response is not necessarily hard, and it doesn't go from easy to hard, because they don't want people to pass or fail. They want some people to get a 0, some to get 1, some to get 2, some to get 3, some to get 4s, and some to get 5s. So on both the multiple choice and the free response, there are easy questions. And it doesn't go from easy to hard. It'll be hard, oh, easy. And same on the free response. It'll be like something really hard and then something so easy that physical science can answer it. So and what they're trying to do is they're trying to shake your confidence, and they'll give you a hard one. And then they know y'all are all smart, and they know one of the things smart kids do is overthink it and doubt their answers. And it'll be an easy question, and the smart kid will read so much into it, they'll make it hard and get the wrong answer. Y'all know what I'm talking about, don't you? So watch out for that. That sometimes you'll read it and you'll go, that can't be that easy. Yes, it can. It can absolutely be that easy, because they want some easy, some middle, some hard. You know, it's not all hard. There's a lot of it right now. If you took it today, you would not make a 0. Now, I don't think you'd pass, but I bet a lot of y'all could get a 2. So we just got to get you up to 3s. Okay? All right, good questions. All right, molecules with expanded valence shells. Atoms that have expanded octets. Make sure I'm on the right line here. No, I'm not even on the right page. Oh, I am on the right page. Have more domains, trigonal, bipyramidal, or I'm on the wrong line. It has 5 electron domains, trigonal, bipyramidal, or 6 octahedral. So it's more, it could be like more than that. Okay, so this is my toy here. So I was getting this question from somebody yesterday. It might have been this class, it might have been the other one. And it was like argon. And they're like, this is saying it's got more stuff bonded to it, but it already has a full valence shell. How can it have more things than 8? It's violating the octet rule, okay? And it can happen. So things can actually have more than an octet. And when it's a noble gas, they used to say that noble gas were inert, that they never reacted. But now they found that if they put them under pressure in extreme situations, you can get them to react, but usually they have more than an octet. Another thing is these geometries, my dog toy here, where you can have these shapes where it's got the trigonal planar around the linear, or it's got the plus sign around the linear. So this would be 5 domains, and that one is 6. Okay, everybody envisioning that with my pretty dog toy there? Okay, so let's talk about what shapes does it make when it has this situation. So if it has 5 domains and they all bond, it makes trigonal bipyramidal. So that's where you've got the Mercedes symbol around the line, okay? And then, so our example for that one is PCl5. Okay, now if you have 5 domains, 4 bond, and one's an unshared pair like this, and our example is SF4, it's called the seesaw. Because remember, we don't look at the non-bonding pairs, we just look at what it makes. And if you look at this, if I take away, I've got my 3, but then one of them is non-binding, and we'll pretend like the 2 together is non-binding. Do you see how it can be a seesaw? You see that? Let me put on my desk. See? It's a little kid seesaw. Everybody see it? Okay. So that's seesaw. So that, like that name seesaw, you will need to know. Trigonal bipyramidal, you need to know that. Okay, next page. Y'all are doing good so far. Okay, so now if we have 5 domains, 3 of them make bonds and 2 don't, then you get T-shaped. So it looks like the letter T. Can everybody see that in the picture? Does the picture make sense to you? Our example is ClF3. Okay, and if we have 5 domains and 2 bond and 3 don't, so we could have these ones around the middle not bonding and the stick going through bonding, then that is just simply linear. Because you don't look at what doesn't bond for the final shape, you just look at what bonds. And so there's one of those where a noble gas is being forced to bond with fluorine. Very unnatural. Yes?
On the test, is it going to ask us to find out which element it is?
I don't understand.
They showed us that image and they asked us, would they ask a question to find out?
Like match these to those?
Yeah.
I don't know. We'll look at some practice tests and we'll see. Okay, and we'll keep, Matt, put a little star on your notes or something to remember when we're reviewing for the test to look, because we have all those AP multiple choice test banks on the AP Classroom, and I also have other sample tests that we'll be looking at. Okay, what about 6? So 6 is my dog toy. They're all bonding. It's our octahedron. That's fun to say. 6 bond, none don't. There's the octahedron. And here is an example of a chemical that does that. If you have 6 and, whoops, that is really bad. Whoop, whoop. And 5 bond and 1 doesn't, then you just would take away one of these. It's square on the bottom and a point, so that's a square pyramid. Can everybody imagine that? Little square pyramid there. Okay, so our example chemical of that is BrF5. And then if you have 6 domains, 4 makes bond and 2 don't, you get just the plus sign in the middle, and that's called square planar. And here is another. So notice that a lot of these have had noble gases. These are not real common things, but they are things that exist, that they used to say didn't exist, and now it does, because they forced it to exist and all that. All right, now what about larger molecules? And they did have a question like this on last year's AP test. Remember, normally they take a long time before teachers or anybody can see an old test, but last year it was leaked in China. And then they released it very quickly after it got leaked. I think I saw it within a week. I'd seen the test. So after, not before. I didn't pay the $5,000 to see it early, but and I wouldn't. Okay, so what about if you have a larger molecule? What you do is you cut it up and you look at the parts. So if we cut right here, this is carbon with 4 domains, so that would be a tetrahedral, right? Okay, and those would be 109.5. If we cut it here, there are 3 domains, so what would that be? 3 domains, they're all bonds around that carbon. What would it be? Starts with a T. Looks like Mercedes-Benz. Trigonal planar. And so that's about 120 degrees. Whoop, whoop, more fun with sound effects. And here we've got oxygen with 4 domains, 2 are unshared pairs, and 2 are bonds. So it's roughly a tetrahedron. Close to 109.5, but if we look at just the shape, it would be bent. Without the unshared pairs, it's bent. This is not going to be a straight line in real life. That's going to be bent. Can you imagine that? Okay, good. You are doing great. Can I roll on? Has everybody got this? Not yet. Okay. That means I get water. Water break. So next we're going to talk about polarity. Those of you who had corn, did she teach you about polarity? Corn people? Yes, I see yes. Okay, good. Okay, can we roll now? Yep, okay. Okay, polar molecules interact with electric fields. Binary compounds are polar if their centers of negative and positive charges do not coincide. So what this means is something is polar if it has a positive side and negative side. Even if bonds have a positive end and a negative end, the molecule will not be polar if they cancel each other out. If everything is equally balanced in all directions, it's nonpolar. So let's look at that. Let's see if y'all can remember this and predict it, okay? So here I've got carbon dioxide. The bonds are polar. Is the molecule polar? What do you think? Polar or nonpolar? Nonpolar. Why? Because they just cancel each other out. Do you see that? This one's going that way. This one's going that way. They are exactly even and balanced. Can you see that? So this is CO2, and it's drawn here what it would look like a little bit more in real life. Okay, so it doesn't have a positive and a negative end. Okay, this is water. Is that going to be polar or non-polar? Polar, because you can see it's positive over here and it's negative over there. And it would look kind of like that if you could just see it. Okay, let's try another one. Hydrogen and chlorine. Is that going to be polar or non-polar? What? HCl, some good old hydrochloric acid. What, is it polar or non-polar? I think somebody said it. It's polar. You can see it's going to be more positive on this side, more negative on that side. It has a positive side and a negative side. Okay, how about methane? Polar or non-polar? Actually, that's CCO4. It is non-polar. Why? They all cancel out. Do you see that? It's exactly symmetrical. Everything's pulling evenly. How about ammonia? Polar or non-polar? It is polar, right? And we know it's got a big negative blob on that side. It's positive on that side. We can tell that by the way those little hydrogens are being bent away. Okay, how about this one? Hydrogen in the middle, 3 fluorines equally around it. Non-polar, y'all are doing awesome. This is BF3. Okay, how about that one? Polar or non-polar? Polar. It's got a big old thing there. A big old chlorine, highly electronegative. It's negative on this side, it's positive on that side. Okay, can you get at this? This is easy, right? Okay, let's go on. Okay, now what about, let me tell you about what bonds look like. Okay, so covalent bonds share electrons of adjacent, they have to be next to each other, atoms. Now, what do those look like? If they are sharing electrons with s orbitals, it looks like that. So they're going to have one s and another s. They overlap, they just sort of squish into each other, and there's a bond. Okay, so remember our orbitals, if the electrons being shared are coming out of the s orbitals, that's what it does. Well, what about if one of them is an s and the other one's a p? Well, then it does that. So an example would be like HCl. The H is s and the Cl, it's a p orbital that it shares. And there it is, make a little bond there. Okay, and so what if it's 2 p orbitals? They line up like that. So example of that would be like chlorine gas. It's got its unshared pairs. But that's how it shares on the end, like that. Can you imagine those? So that's how it shares. So look, that's something new you've never learned before. You never learned what these bonds look like. Unless Miss Corn taught you, did she teach you this? I hope not, because I want you to learn something new today. Okay, the next idea. When you have these covalent bonds, imagine right here. If you squish these too close, those positive nuclei are going to repel each other and not be happy. If you pull them too far out, not enough sharing is going on and it's not going to be happy. So there's an optimal distance, and it is this. So optimal distance. So this was on last year's AP test. And it was a little graph like this. It kind of looks like this. Whoop. And then it kind of goes up to here and then to there. And we have 3 places. And the question says, which one is showing you the optimal distance? And it's that one. Such a fancy looking question to be so easy. That means that's the sweet spot right there. Right here, no good. Over there, no good. Too close, too far away. It's got to be just right. That's what that little graph showing you is just right. Okay, can I scroll it? Yes? Okay, we are almost done. We're getting there. Come on, scroll. Okay. Now, this is another thing you don't know. So fun to not be bored. Okay. There is something called hybrid orbitals. What does hybrid usually mean? Like a hybrid car. What is it? What is it? It's a mix. So these are mixed. And you're like, what? So we've learned about S, P, D, and F. And in your head, you thought, never will these be different. But you were wrong. What they do is they will mix the orbitals and make something new. Okay? So, to apply the idea of orbital overlap and valence bond theory to polyatomic molecules, we need to introduce the concept of hybrid orbitals. Okay, so let's look at beryllium. Somebody tell me the electron configuration for beryllium. You can sing it if you want to. I scared you about this thing. What is it, Kevin? 1s, oops, I'm turning it on. 1s2, and what is it? 2s2. Okay, that is what you would think it is. Okay, but where atoms make bonds is where you have a box with only one arrow in it. And that would mean that beryllium can never make a bond. It can never make a covalent bond. But it does. So if it was this, it would not be able to form bonds. But we can see right here it's making bonds. So it doesn't. So what it does is it says, you know, if I bump this one little electron up, then I can make 2 bonds. So it promotes an electron. And look at that. So here it is promoted. So it would promote one up. So now it can make 2. Everybody with me so far? I think I got to know. Let's go over it again. Beryllium's what you've been doing for its orbital diagram is 1s2, 2s2. But if it did that, it couldn't make any bonds. And it wants to make bonds. It has a deep desire to make a bond. So it said, you know what? I'm just going to bump up one of these electrons into a P, and now I got 2 boxes with only 1 arrow ready for 2 bonds. Okay, now we okay so far? But that's not where it ends. Not only does it want to make bonds, nature likes what? Balance. And these are not the same. And it wants them to be the same, so it decides to mix them. It's going to mix them and make a Frankenstein. Not S, not P, but something new. And it is called SP, and they're identical. It's not S, it's not P, it's SP, and we got 2 of them. And that's what it does. Yes, Kevin?
Why does it get promoted?
Because it wanted to make bonds. It wanted to do this. And it has the ability to do it, so it did. It wanted to bond. The beryllium wanted to make those bonds with the fluorines. Now, The bottom line answer of why it wants to, that you write on the AP test, is energy. The reason why everything in chemistry happens is energy. It is more optimal energetically. The answer is just always energy. Yes?
So why do the boxes go from 1 and 3 to 2? Because they go from 2s2 and 2. Well, I get just 2s having 1 box, 2p having 3 boxes.
This is what it normally has, right?
Yeah.
Normally it's that. But now what it's going to do is it's going to take these two and mix them together till they're exactly the same and they're SPs.
Okay.
Because it wants balance. It wants them to be the same.
So there will always be 2 boxes there?
Well, we're going to talk about that. No, there'll be some more. So that's one way it can mix it. So when this happens, mixing the S and the P yields degenerate, and I think that's kind of unkind to call them degenerate orbitals. But that's what they call them. I didn't get to name them. They're degenerate. They're Frankenstein. So I put DX on here. There used to be wrestlers in the early 2000s called D Generation X. Triple H and, what was the other guy? Shawn Michaels. So I put DX on there because they're degenerate. Anybody know about D Generation X and old wrestlers? No? Do you know about new wrestlers like Kevin Owens? No? Nobody? No? Royal Rumble's coming up. It's a lot of fun. Okay, so this is how it works. We have S and a P, and they get mixed together to make 2 of these SPs. You see, S plus P makes that. These are the monsters. The SPs. Ah! Okay, and now they're exactly alike. It's mixed like chocolate milk. These 2 degenerate orbitals align themselves 180 degrees from each other and 90 degrees from the remaining unhybridized p orbitals, and it makes a beautiful linear molecule. Look at that. No wonder it wanted to do that. That's so pretty and symmetrical. Of course it wanted to do that. Okay, well, what about other ones? This was Mr. Sanchez's question. So what about SP2? So this is what happens sometimes. So if we had 2S and 1P, this is called SP2. Before we did SP, this is SP2. We can promote one of them, so this is original. Here it is promoted. So now we can have this. How many bonds can this one make? It can make 3. Do you see how 3 only have 1 arrow in it? But then we mix them, and they are called SP2s because we mixed 1 S and 2 Ps, and we have 3 SP2s, and this is our mix. The more you do it, and the more you look at the little pictures, the more it'll make sense. Okay, so if there's SP2, what do you guess there is also? SP3, yes. So this is what carbon does. So carbon, we normally think of carbon as that, as only making 2 bonds, right? But we know, you've learned that carbon can make 4 bonds. So how does it do it? Mixing. So we take that one and promote it. But we want them to all be exactly loopsy the same. So S and P mixed together is going to make 4 identical sp3 bonds. So that's kind of fun. Learning something brand new. Unboring and interesting. Okay, this is definitely college level chemistry. This is not high school, this is college. All right, let's move on up. Can I scroll? Good, yes, okay. All right, so here are some pictures of it. This is an S, that's a P, that's a P. They get mixed into 3 sp2s, and there it is, what it would look like. Okay, so here's another one. Here we've got an S, a P, and a P. They get mixed into sp3s, and then that's what it would look like. So do you understand these drawings a little bit? Good. Can I scroll? I didn't really write anything new. It was already on there. I labeled those. That was new. That was it. Okay. So our geometries involving expanded octets on the central atom. To do that, we used orbitals in our hybrids. So this goes back to the thing where they were going, how can it be that we have more than 8? It's because they're mixing stuff, and they're opening up orbitals for mixing. That's where they came from. How does that xenon make more than 8? You have more than an octet? It's mixing. It's mixing stuff and opening up orbitals for bonds. That's what it's doing. So like our dog toy, that was with 3 around, that's with 4 around. It's called hypervalent. It's got more than 8. See, 2, 4, 6, 8, 10, 12. It's got more than 8.
Wait, why is there the dog?
Because I have a dog toy. This is what we look at. So this is hypervalent. It's got more than 8 electrons around it. I have to draw something, so I drew a doggy. Okay, so my dog toy. Okay, once you know the electron domain geometry, you can know the hybridization state of the atom. Okay, so that's our last little bit of that. So now we want to talk about multiple bonds. I started off with making you make a triple bond. Well, what do these look like? Okay. The covalent bonds we've seen so far are sigma bonds, characterized by single, strong overlap. So these single bonds are really strong. They're called sigma bonds. But what about double bonds? Then it's something called pi bonds. Pi bonds. So this is double and they're used in double and triple. So how do those work? See, don't you feel smart learning about sigma and pi bonds? So pi bonds look like this, okay? They are characterized by overlap above and below the axis. So before we were right on the axis. But now, for a double bond, then you get this above and below. Now, this is not the double bond. This is one bond, but it's just the area where this pair of electrons can be is above and below. You can see it better here. So there would be one sigma bond in the middle here, in between, where it's just this little single bond overlap. But these p orbitals are going to overlap, and these two p orbitals are going to share one pair of electrons, but where they can hang out is above or below. This is the area the pair can hang out in. It's like a 2-room apartment instead of a 1-room apartment. We still doing okay? All right, good. So, single bonds always sigma bonds, because sigma overlap is greater, resulting in a stronger bond and more energy lowering. So when you're looking at reactions and you want to know where a reaction is going to take place, it's going to take place at a double bond because that's weak and breaks. So just know that. It's awkward. It's poked up and it's down below. It's ready to get attacked and broken. Okay. So here is sort of a bigger picture of it. You've got the single bond, the first bond in the middle, the sigma, and then the next bond you've got right there on both sides. So one pair gets to hang out here, and another pair gets to hang out on top and on bottom. Can you see that? I'm getting lots of scrunched up faces. Okay, so now let's talk about a triple bond. So here's an example of that double bond right there, what it would look like. So here is a triple bond. You've got the single bond in the middle, and then these two P's can go above and beyond here, and these two P's would share right there. It'd be like sticking another one of these shapes like that. Can you kind of imagine a little bit? Maybe we can find some video. Maybe there's some good videos for this, because it almost needs to be illustrated dynamically for you. Okay, so delocalized pi bonding. When writing, so we're going to talk about resonance for a second. When writing Lewis structures for species like the nitrate ion, we draw resonance structures to more accurately reflect the structure of the molecule or ion. So let me explain what that was. Back in the dark ages of the 80s, when I was in high school, they explained resonance like this. That this double bond could be here, here, or here, so it quickly goes chick, 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 and zips in between them, changing from one to another quickly, like vibrating back and forth. But that's wrong. Instead, it's more like it gets smeared evenly between them. That instead of being 1, 2, 3, 1, 2, 3, 1, 2, 3, it's just one with something else. Okay? So what it does is it sort of smears it around, which you can kind of see illustrated there. Okay, so the p orbital on all three oxygens overlap with the p orbital of the central nitrogen. They're all doing a little bit of sharing, yes.
You talking about the idea that the electron would have moved made me think about that. Isn't it when an electron is moving between atom to atom that it's creating electricity?
Electricity is mostly created over here when these, this goes back to our metals, when these loose electrons that are not assigned to any nuclei flow along. And when they do it, it's like you've got all of them sitting right here. But now I add an electron over here from my battery, from my voltage, and it makes everybody go, oh, and they all shift along. This one pops out over here. And then it comes back in over here, and it pops in, and everybody shifts, and he pops out. That's electricity. It's an event. Okay, so not exactly. And this is more just how, instead of going 1, 2, 3, it just smears, it mixes between them all. So like when I was in high school, they said benzene, remember this, wherever it's a corner, it's a carbon. And if it doesn't have 4 sticks, the fourth one is a hydrogen. They said it was like the bond's here, and then it switches to here, and then it switches back to here. But now we know, no, it's that they're all sharing it together. And so it's smeared around like that, so they'll draw it like that instead. Okay, what do you think? Unit 2. Okay, let's end the video. Science is great.